Back in the 1960s, Pratt & Whitney ruled the skies. Riding high on Boeing's success, it dominated commercial aviation. Its booming profits sent a loud message to the engine world. Forget the battlefield. Civil aviation is where the real money flies. Across the Atlantic, Francis Snecma, fresh off building engines for the Concorde, was eager to join the race. They aimed to create a mid-thrust turbofan to take on Pratt. But Concorde's commercial flop had left scars. Snecma didn't dare go it alone. They needed a partner. A strong one. Looking around, Rolls-Royce was too busy saving itself from bankruptcy. Globally, there weren't many who could build jet engines at this level. After much thought, the French turned to a giant, General Electric. At that time, GE was a military powerhouse with limited presence in civil aviation. But it too was looking for a way in. At the 1971 Paris Air Show, while the Soviet Tu-144 roared overhead, Snecma quietly approached GE1 meeting, a few glasses of red wine, and the deal was born. They shook hands on a plan to co-develop an engine, with shared costs and shared dreams. 3 years later, the first engine was born, the CFM56. It wasn't smooth. French romance and American risk-taking clashed more than once, sparking intense friction that at times threw the future of the CFM56 into doubt. But no one expected what happened next. In the decades that followed, this engine didn't just compete. It took over the jet engine market with near-total dominance. To date, over 33,000 CFM56 engines have been delivered. Roughly 28,000 are still flying. From Boeing 737s to Airbus A320, from the KC-135 tanker to the P-8A patrol jet, a plane powered by a CFM56 takes off every 2 seconds somewhere in the world. It has logged over 1 billion flight hours with a mind-blowing 99.96% reliability rate. In China, where maintenance is top-notch, that number reaches 99.99%. That's not just engineering, that's magic. Its design philosophy has shaped generations of engines. Even China's WS-10, the engine for the J-20 stealth fighter, traces distant roots back to the CFM56. Half a century has passed, but CFM56 still roars across the skies. In the aviation world, it's often called the most perfect engine ever built. That's not just praise. That's the heartfelt respect of thousands of pilots, engineers, and airlines who trust it day after day. Unlike today's engines with fully independent designs, jet engines for passenger planes in the 1960s were mostly modified versions of military models. For example, the Boeing 707, which truly brought civil aviation into the jet age, used the Pratt & Whitney JT3C engine. This engine was actually based on the J-57 turbojet made for the US Air Force's B-52 bomber. The advantage was clear. You didn't have to start from scratch. This saved time and cut development costs, but the downsides were serious. These half-military engines burned a huge amount of fuel and weren't very reliable. They often gave passengers and pilots a mental stress test mid-flight. They also ignored environmental and noise regulations, focusing only on brute force. Using military bones to build civil wings was the shortcut of early jetliners. Pratt & Whitney led the way by launching the JT-3C from the J-57 and the JT-8D from the J-52. Military and civil models grew together, but as fuel prices rose and regulations tightened, civil aviation needed engines built for its own future. Francis Snecma, now known as Safran, began developing a new 10-ton thrust civil engine in the mid-1960s. They were among the first to realize that the gap between civil and military engines would keep growing, so they hoped to use some military technologies, add their own innovations, and design a new engine with lower noise and better fuel efficiency. This engine was called the M56. As the project moved forward, Snecma realized they lacked strength in R&D, manufacturing, and marketing. Without help, the project would surely fail. They decided to look for a partner to co-develop, produce, and sell the new engine. At the time Pratt & Whitney dominated, Rolls-Royce was in bankruptcy, leaving GE the only option. Coincidentally, GE envied Pratt's success, hating others' profits more than its own losses. And with both leaders being World War II veterans, they clicked at their first meeting. A cross-border partnership naturally formed. Each side invested 50% and combined GE's civil engine code CF with Snecma's M56 to create the CFM56. Early talks went smoothly, but real problems emerged once work began. After GE joined the project, they aimed high. To show their sincerity, they offered the core technology of their F101 engine. The F101 was the most advanced engine of its time. It powered the B-1 Lancer supersonic bomber and outperformed all its peers. It used a 9-stage high-pressure compressor. The first stage blades had a transonic airfoil design. Their tip speed reached 400 meters per second, about Mach 1.44, nearly 1.5 times the speed of sound. This enabled a high-pressure ratio and boosted fuel efficiency. In the turbine section, GE developed high-temperature resistant blades and precise internal cooling channels. These features helped the core turbine run stably in gas flows close to 1600 degrees Celsius. As a result, it lasted longer and needed fewer overhauls. This military-grade core provided a solid foundation for the CFM56, but when GE applied for export approval from the US government, they were immediately rejected. The reason was simple. The F-101 was tied to the B-1 Lancer, a key part of US strategic deterrence. It had also received heavy funding from the Department of Defense. In short, the answer was, pay more. This decision shocked the French side and almost killed the entire project. Luckily, the French government valued this partnership highly. President Georges Pompidou personally lobbied US President Nixon whenever possible. GE also had its concerns. If the deal fell through and SNECMA finished the engine alone, GE might lose its chance to enter the market at all. So General Electric stepped in and joined the lobbying efforts as well. Eventually, at the 1973 US-France summit, both sides reached a hard-won agreement. It's said that France paid a heavy price to gain US approval. The engine's core had to be built in the US and shipped to France. There, GE engineers assembled it in isolation rooms. French staff were not allowed to participate at all to prevent leaks of sensitive technology. This fragmented process worsened friction between the teams. They disagreed on standards, switched constantly between imperial and metric units, and even struggled with engineering language. On top of that, France had to pay $80 million in licensing fees as compensation for development costs. More importantly, the French government promised not to impose tariffs on future US aircraft imported into Europe. Fortunately, the deal worked. The US finally approved the use of F-101 technology for the CFM56 project. Since GE had offered its best, Safran couldn't hold back either. SNECMA handled the front fan and low-pressure turbine, designing them from scratch for civil use without copying military designs. They designed 44 wide-tip titanium blades, each shrouded 1.73 meters across, providing 78% of thrust. Blade shoulders cut airflow separation and vibration, boosting low-mid-speed efficiency and raising the bypass ratio to 5.1 to 1. This high bypass layout saved fuel, reduced noise, and drove the CFM56's strong economics. More importantly, the CFM56 was modular from the start. If a blade was damaged, it could be replaced without removing the whole engine. This greatly reduced maintenance time and cost. The modular design also allowed for a global training system. Airline technicians could use standard manuals to learn module removal and inspection, improving airworthiness and efficiency, and still an industry benchmark today. In 1974, as development neared completion, Safran and GE signed the final agreement to form a joint venture. They named the company after the project code, CFM International. In June that year, the first CFM56 engine was tested on a stand. As the gears inside turned, so did the gears of aviation history. Beyond its design, the CFM56 took a bold step in sales strategy. Due to the high risks from massive development costs, civil jet engines used to be built only after securing firm orders. Every engine had a buyer before it was born. But the CFM56 did the opposite. It became the first engine developed before having any customers. When CFM International finally launched it into the market, they found that almost every airliner had already picked a favorite. No one wanted to take in this single noble. In the following years, even with several rounds of ground and flight tests, the CFM56 still failed to win the hearts of commercial airlines. Market response remained cold, and the project was close to being shut down. At the critical moment, a military order CFM least expected saved the engine. In 1977, the US Air Force, fed up with the old Pratt and Whitney J57s, began re-engining KC-135s. How bad were they? Before takeoff, crews had to pump 2,500 liters of water into each engine just so the plane could lift off. It was practically the jet engine world's GP2. Having invested heavily in the CFM56 project, the French government seized the moment, announcing that France's 11 KC-135s would skip bidding and re-engine with the CFM56. The results were clear. Thrust nearly doubled over the J57, and fuel use fell 25%. This let the KC-135 cut takeoff by 1,100 meters, add 1,000 kilometers range, climb 900 meters higher, and sharply reduce noise. The US Air Force was shocked. They cursed the old Pratt and Whitney engines, then ordered all 500-plus KC-135s refitted with the CFM56, over 2,000 engines at once. 5 years after CFM's founding and 8 years after project start, the CFM56 got its first major order. With the military leading, airlines saw engine swaps were possible. In March 1979, United Airlines became the first, upgrading 30 DC-8s with the CFM56. This marked its entry into civil aviation. From then on, CFM had stepped into commercial flight. But retrofits were small. What really lifted the CFM56 was the aviation giant Boeing. In 1980, to meet customer demand and stricter noise and environmental regulations, Boeing launched its first major upgrade of the 737 series, moving from the 737 original to the 737 Classic. At that time, in the 10-ton class, the CFM56's only rival was Pratt & Whitney's old JT-8D. The result was clear. Boeing chose the more advanced CFM56 for all 737 Classics. Due to the 737's naturally short landing gear, its wings sit close to the ground. So engineers had to make several changes to the engine. They reduced the fan diameter, which lowered the bypass ratio. They also moved the accessory gearbox from the bottom to the side. This gave the engine a unique flat-bottom shape, which became a visual signature of later 737 models. This version of the engine was named the CFM56-3. Although these changes slightly reduced its thrust, the CFM56-3 still far outperformed the older JT-8D, especially in fuel efficiency, noise levels, and reliability. Its performance gave Boeing engineers new design freedom, ending JT-8D limits. The 737-300 was 2.9 meters longer than the 737-200. It could carry up to 149 passengers. It also had more room for electronics, bringing a major upgrade to the 737's cockpit systems. The later -400 variants went even further, offered larger fuselages and cargo bays. They also improved aerodynamics. These changes boosted handling, safety, and fuel economy. The numbers told the story. Boeing delivered 1,988 737 Classics, cementing the CFM56's expansion into civil aviation. In the 1980s, Airbus announced a new narrow-body aircraft, the A320, directly targeting the Boeing 737. With half European roots and US success, CFM aimed to return home in glory. At first, CFM planned a CFM56-4 based on the Dash 2, but this time the competition wouldn't be easy. The CFM56 was no longer facing the outdated JT-8D. Its new rival was a next-generation engine built by global aerospace giants, the IAE V2500. Behind the IAE stood a luxury dream team: Pratt & Whitney from the US, Rolls-Royce from the UK, MTU from Germany, and Japan Aero Engines, each a giant in its own right. Pratt handled the high-pressure turbine and combustion chamber. Rolls-Royce did the high-pressure compressor. MTU took care of the low-pressure turbine. Japan managed the fan and low-pressure compressor. They combined strengths to push fuel efficiency even further. With bold innovation and a star-studded team, the V2500 looked great on paper. It made the CFM56-4 seem outdated. Wait, am I the JT-8D now? Facing this challenge, CFM dropped the 56-4 plan without hesitation. Instead, they redesigned the engine from the inside out and introduced the all-new CFM56-5A. The upgrade had 3 key changes. First, the fan and compressor used 3D aerodynamics for better, more stable airflow. Second, improved aerodynamics raised fan efficiency, letting engineers cut blades from 44 to 36, reducing weight 15% and noise. Most importantly, they added FEDEC, the full authority digital engine control. First seen on the PW2000 for the 757 and soon standard on all modern engines. FEDEC combines control algorithms like PID and MPC. It's like giving the engine a brain. It controls fuel injection and thrust response to the millisecond, optimizing output at every stage for better efficiency and precision. Even with these upgrades, the CFM56 kept its legendary reliability and easy maintenance, the key to turning the tide later. As the A320 entered service, airlines gradually realized something. Though the V2500's innovations promised better fuel burn, its complex structure caused a spike in maintenance costs and failure rates. Even a simple repair required removing the whole engine. Each service could take 2 to 3 days. MTU even built a dedicated repair line for the V2500. One engine was enough to feed a whole business. In contrast, the CFM56 stuck with its modular design. A single fan repair usually took just 8 hours. In fast-paced airline operations, that made all the difference. Later, CFM developed the CFM56-5B for the A321, using a dual annular combustor. The inner ring worked during cruise. The outer ring kicked in for higher thrust. The engine could switch between them automatically, further improving fuel burn and cut emissions to meet EU standards. In decades of real-world operation, the CFM56-5 series could fly up to 14,000 hours before its first overhaul. Even after overhaul, it still ran over 10,000 hours stably. A typical A320 flies about 3,500 hours a year, so one CFM56 could fly nearly 4 years without needing a shop visit. That left its rivals far behind. Even though it didn't win on paper specs, the CFM56 came out on top with better reliability, easier maintenance, and lower lifetime cost. It beat the V2500 and became the main engine of the A320 family, taking over 60% of the market. And of course, when talking about the CFM56-5 series, one engine can't be ignored, the CFM56-5C. It had a huge 1.85 meters fan, a 6.5 bypass ratio, an extra fifth stage in the low-pressure turbine, and 151 kilonewtons max thrust. It was the strongest in the entire CFM56 lineup. The engineers tried their best to push it to the limit. But there was one problem. The 5C was built for the wide-body A340. The first-generation A340 came with 5 APUs. Well, not really. It had 4 engines, but not out of necessity. It was more a reluctant compromise with the regulations. To fly across oceans, Airbus had to install 4 engines to meet the regulations at the time. But when IAE suddenly backed out, the A340 was left in an awkward situation with no engine to use. Still, there's nothing 2 CFM56 can't fix. And if 2 aren't enough, just add 2 more. So the CFM56 became the emergency power source for the A340. Though the 5C reached technical heights, it still couldn't fully handle the A340's demands for long range and heavy loads. The result? Weak takeoff, poor climb, and a reputation as the least loved variant. It reminded people of the JT-8D on the KC-135 and became the least liked version. But once CFM left the A340 and returned to its narrow-body comfort zone, a true legend was about to be born. In the 1990s, the A320 series gained market share with fly-by-wire and better fuel efficiency. Boeing could no longer sit still. They launched the second major upgrade of the 737 series, the 737 Next Generation. The new aircraft targeted what airlines valued most: better fuel efficiency, longer range, more seats, and strong performance in complex global environments, aiming to reclaim its voice in the narrow-body market. Given the CFM56's solid performance on the 737 Classic, Boeing again chose CFM as the sole engine supplier for the 737 NG. Learning from the V2500 experience, CFM didn't go for flashy features. Instead, they focused on what airlines actually needed. This led to the CFM56-7B, a product built on practical thinking. The biggest improvement in the 7B was its fan blade design. It used a controlled diffusion airfoil, or CDA blade. With help from CFD analysis, the blade's thickness and curvature were fine-tuned. This made airflow smoother and reduced boundary layer separation, which significantly improved aerodynamic efficiency. The wide-chord blade had a thicker leading and trailing edge. It was structurally stronger and more resistant to corrosion and bird strikes, but it was also heavier, putting more centrifugal load on the disc. Most engines would solve this by using advanced, lightweight hollow blades or composite materials, but after repeated tests, the CFM team found a simpler solution. For a medium-thrust engine with a fan diameter of just 1.6 meters, reinforcing the disc was enough to handle the solid blades. Thanks to aerodynamic improvements, the fan now needed only 24 blades. That was 20 fewer than the original CFM56. This made manufacturing and maintenance much easier, and struck a perfect balance between performance and cost. Also, back in the F101 engine, GE had already used advanced single-crystal nickel alloy turbine blades. They were extremely resistant to high-temperature fatigue and considered a masterpiece of materials engineering, but the cost was too high for use in the CFM56 series. For engineers, it was the one dream they couldn't touch. Now, times had changed. With progress in materials science, the CFM56-7B finally brought this dream to life. Its high-pressure turbine blades were upgraded to GE's second-generation single-crystal nickel alloy. In addition to nickel, the alloy also included boron, carbon, and yttrium. Boron and carbon helped extend blade life under heat. Yttrium, a rare earth element, greatly improved thermal fatigue resistance at high temperatures. With this, the CFM56-7B was now using the complete version of the F101 core. Its durability reached a whole new level. It's worth mentioning that the CFM56-7B also tested a serrated nacelle design to reduce noise. Surprised? The first to try a serrated nacelle wasn't the Boeing 787, it was the CFM56. Though it was never officially used on the 737NG, this experiment laid the foundation for later designs on the 787 and 737 MAX. Thanks to its solid design and outstanding reliability, the CFM56-7B gave the 737NG excellent adaptability. From short-haul high-frequency routes to high-altitude, high-heat, high-humidity, or extreme cold, the 7B stayed steady and strong, which fit narrow-body operators like a glove. This civil engine even returned to military service, withstanding vibrations and salt spray, and became the standard for the US Navy's P-8A patrol aircraft. Maybe the only thing it couldn't withstand was the decoy flare from the J-16. This fly-a-lot, break-a-little reliability proved itself in commercial service. In 2014, a Xiamen Airlines 737 with a CFM56-7B ran 9 years, 27,458 hours, and 19,491 cycles before its first shop visit, setting the CFM56 record for longest pre-overhaul service. This proved its safety and lowered engine cost per hour, boosting airline profit. With the CFM56-7B, Boeing delivered 7,110 737 NGs worldwide, with a fatal accident rate of just 0.09 per million flights. It became one of the safest, best-selling aircraft ever. In the brilliant CFM56 family, the 7B may not be the most powerful, but it's the one that fits real-world airline operations best. The CFM56-7B wasn't made to show off technology. It was made for the airline's daily balance sheet, and that's exactly why it became the most widely used turbofan engine in aviation history. In fact, the CFM56-7B's success is just one chapter in the CFM56 legend. From the very beginning, it had no customers, no platform, and nearly died before it was born. Yet today, it has become the most widely used civil turbofan engine in the world. What drove this transformation wasn't just technical breakthroughs. It was a deep understanding of reality and a relentless pursuit of reliability. The CFM56 never showed off, yet it always stood firm in times of change. It never rushed ahead, yet its full life cost kept winning airlines over. It never chased the spotlight, yet kept evolving in small, steady steps to meet new rules and new demands. Looking at today's aviation world, Pratt & Whitney bet big on GTF engine and nearly lost it all. Rolls-Royce just can't let go of its 3-shaft turbofans, and the one that was called conservative CFM has quietly become the king of narrow-body jets. Thanks to steady upgrades and flexible strategy, the CFM56 still remains under the wing, flying high above the sky. You may never find the CFM56 breathtaking, but it always flies, always fixes, and always earns your trust. But no flower blooms forever, and no engine stays young. Now in its 50s, the CFM56 is starting to feel the weight of a new era. So how did CFM respond? Stay tuned for the next episode of Engines Past and Present. CFM Leap, a giant leap, one steady step at a time. See you in the next video.